Hello everyone. Today we'll discuss about serial communication in LPC2148. So before going to see something about serial communication, let us see what is a communication. So communication is nothing but transfer of information or data between two entities, two machines, two systems, or two endpoints is nothing but communication. And if you look into the classification of serial communication, now it is classified into two types. One is synchronous serial communication and the other one is asynchronous serial communication. So what is serial communication? So it's nothing but transfer of data in bit by bit manner is nothing but a serial communication. Now what is this synchronous serial communication? What happens in that? So in case of synchronous serial communication, both the devices, here we call both the devices as master and slave. So they will share or they'll have an dependent clock. So master generates a clock and the same clock is given to the slave as a clock input. So the clock between the master and the slave is dependent. But when it comes to asynchronous serial communication, now both the devices like transmitter and receiver will have a separate clock, or else I can call them as individual clocks or independent clocks, but the clock value should be same so that they can communicate with each other without any loss of data. Okay, so we'll discuss how to achieve this serial communication in LPC2148 by using UARTs. Okay, so in case of LPC2148 we have two UARTs, namely UART0 and UART1. Okay, so let us see what are the registers that we need to access in order to use the serial communication in LPC2148. Now, these are the registers which we need to access to use the basic functionality of UART. Okay, now as I said, there are totally two UARTs and we have to represent them by using U0 and U1. So if you are using UART0, then the register should be named as U0 with the register name. If you are using UART1, then you have to name the registers, or you have to use the registers with the name UART and then its register. Okay, so these are all the registers which we need to program or which we need to access for using UART in case of LPC2148. So we'll see each and every registers. Okay, we'll see the functionality of each and every bit inside these registers. So let us start our discussion with line control register. Now it's an 8-bit register. Now we'll start from the LSBs. As you can see, the two LSBs 0 and 1, these are used for selecting the character length. So if you're programming these two bits with 0 0, it means you are going with 5 bits per character. So it means you are representing a single character with the help of 5 bits. If it is programmed to 0 1, it means 6 bits. If it is 1 0, 7 bits. If it is 1 1, it means you are using 8 bits for representing a single character. So in most of the applications we do use this 8-bit representation. Why? Because 8-bit representation is nothing but ASCII format. So in most of the applications, or most of the applications will be using ASCII format. So that's the reason in many of the cases, or in most of the applications, they use ASCII format representation. So basically this is a extended ASCII format where we use 8 bits for representing a single character, but earlier we have used on we were using only 7 bits for representing a single character. Now it has extended, so that's the reason we are using 8 bits for representing a single character. Okay, and the next bit is stop bit. So if you're programming it to 0, it means you are using only one stop bit at the end of the frame. Okay, but if you're programming it to 1, then it means you're using 2 stop bits at the end of each and every frame. Now what does a frame include? A frame has a start bit, the message bits, and a optional parity bit along with the stop bits. Now this complete is nothing but your frame. Okay, and the process of adding the start or parity as well as stop bit is nothing but framing. So the output of framing process is nothing but your frame. Okay, so here you can use either 2 stop bits or 1 stop bit by programming this particular bit. In most of the cases we do use this 1 stop bit. Okay, if the peripheral is slower, then we'll be using 2 stop bits. Okay, and then The next bit is parity enable. As you can see, now we'll be using this kind of bit or this kind of parity bits whenever we go with error correction and error detection. So if you want to use parity bits, then you have to enable this, and then you have to use these two bits, or you have to program these two bits according to your requirement. That is, if you want to go with odd parity, then it should be programmed with 0 0. If you want to go with even parity, then you have to go with 0 1. So odd parity is nothing but the number of ones present in the message would be odd number, and even parity is nothing but number of ones present inside the message or inside the frame will be even number. Okay, and then we have one more bit here, that is break control. Now if you are programming this particular bit to logic 1, then what happens here is immediately the THD pin of UART will be forced low for a period of 1 character. Okay, so why do we use this bit? So this particular bit, if it is enabled, then it differentiates words. So what do you mean by word in case of LPC2148? Word is nothing but 32 bits. Okay, but we represent a single character by using 8 bits. So it means after every 4 characters it differentiates, or else it differentiates every 4 characters when it is programmed to 1. So if you are making it to 1, then it will differentiate 4 characters. For every 4 characters, or every 4 characters are differentiated if it is programmed to 1. Okay, and then you have divisor latch access bit. Now if you are making it to 0, then you can access some registers. If you are making it to 1, then you can access some other registers. Okay, if you are making it to 0, then you can access the buffer registers. If it is programmed to 1, then it means you can access the divisor latch registers. Okay, so just for now, just keep it in mind that making it to 1, you can access the divisor latch registers, and making it to 0, you can access buffer registers. Okay, now let us see divisor latch registers. Actually, we have 2 registers like DLL and DLM. So these are the 2 registers which comes under divisor latch registers. Okay, so here DLL is the LSB of divisor latch register, and DLM is the MSB of the divisor latch register. It's a 32-bit register. So each of these DLL and DLM are 16 bits in size. Okay, so we use this formula for calculating the baud rate, that is baud rate equals peripheral clock divided by 16 into U0 DLM plus U0 DLL into 1 plus divide val by mul val. Okay, so for now what we do is, assuming that we want to calculate this U0 DLM as well as DLL for 9600 baud rate. Okay, now we'll assume that this particular term, that is divide val by mul val, is 0. So you'll get something like peripheral clock divided by 16 into U0 DLM plus U0 DLM. So if you rearrange this equation, like, as you know what is a peripheral clock, that is 15 megahertz. Basically we use 12 megahertz clock, 12 megahertz crystal. Now that frequency is given as an input to PLL, and PLL, if we are setting the PLL to a factor of 5, then it multiplies it by 5, so that the output would be 60 megahertz. Now that 60 megahertz will be given as an input to VPB divider. Now that VPB divider, if a value is something like 4 is set inside VPB divider, then it divides the incoming clock, that is 60 megahertz, by 4, and the output will become 15 megahertz. Now this 15 megahertz will be given as an input to all the peripherals. Okay, so we can program that VPP divider value either to divide by 4, or else to divide by 2, or else to the same frequency as the processor is receiving. Okay, but basically we do divide this processor clock, because processor is much faster as compared to the peripherals, and also we want to reduce the power consumption. So for that reason, we'll divide the incoming clock by using VPP divider. Okay, so that's the reason we got here 15 megahertz, which is the peripheral clock. So all the peripherals are receiving only 15 megahertz. Okay, you can program it, and then 16 into 9600. Now this is the baud rate for which I am calculating. So I want to calculate DLL and DLM. In this case, I'm using UART 0, so that's the reason I'm going with U0 and U0 here. So here I've calculated this value. I've got a value something in decimal. I've converted it into hexadecimal. So this is the value which I got. So how to store this hexadecimal value into DLL and DLM? So 61 will be stored into LSB bits, and then 00 will be appended in the MSB bits. So now if you are using this value, then it means that you're going with 9600 baud rate. So this is how we calculate the baud rate, and we place those values into DLL and DLM. Okay, so if you want to access this DLL and DLM register, then definitely you have to program this divisor latch access bit to logic 1. It enables divisor latch registers. Okay, now let us discuss about line status register. Now line status register is again of 8 bits. Okay, now with the help of this register, we'll come to know when to transmit a character as well as when to receive a character. Okay, so let us see. So here the first bit RDR, which is nothing but receive data ready, receiver data ready. So whenever the buffer holds a character, or whenever the receiver buffer holds a character, then this UART will intimate the processor regarding that character. Okay, so whenever the UART receives a character, then this particular bit will become 1, indicating that one character is present inside receive buffer register. Okay, if it is 0, it means that it is still in the process of receiving the character. Okay, so when it becomes 1, then it indicates that UART has received a character from the external world, and now that character is present inside the receive buffer register. It's a buffer register. Okay, and then we have 3 more bits here. These 3 are overrun error, parity error, and a framing error. So these 3 bits are related to error bits. Okay, now overrun error. Now this overrun error results assuming that a peripheral is sending some characters to the UART. Okay, so it has sent some set of characters to UART, but still the processor is not reading those characters. Now assume that buffer is full, that is receive buffer is full. Now what happens, as the peripheral doesn't know the status of the UART, it will send the next character. So this character will override the previous characters and resulting in overrun error. Okay, so this particular condition is generated whenever an overrun is occurred inside the UART. Okay, and then parity error. So this results when there is an error or when there is a modification inside the received parity data. Okay, so it means if transmitter is sending with odd parity, and if the receiver is receiving with even parity, then it results parity error. Okay, and then you have a framing error. Now any modification inside the stop bit will result in framing error. For example, if transmitter is transmitting 2 stop bits, but receiver has received only 1 stop bit, then it results in framing error. Okay, now you have a break interrupt. So as we have break transmission in case of LCR or with respect to the transmitter, now the receiver has to know when the character or when the words are differentiated. So when a word is differentiated, then this particular bit will become 1, indicating that it is a break interrupt. So it has to differentiate. The receiver has to differentiate the next coming 4 characters. Okay, and then you have transmit holding register empty. So whenever the transmit hold buffer register becomes empty, then this particular bit will become 1, indicating that the buffer register related to the transmitter is empty. Okay, and basically we know that inside the UART will have a buffer as well as a shift register. So user can access only buffer register but not to the shift register. Okay, so whenever this shift register has become empty, then this particular bit will become 1, and this is the bit which we need to monitor every time when we want to transmit a character. Okay, so we'll be monitoring this bit whenever we want to transmit the characters, that is TEMT. So if this has become 1, then it means that 1 character is transmitted. Now the shift register is empty. Now error in received before. So if any one of the errors are resulting of, or else if any one of the errors are resulted, or if any one of the error is generated, then this particular bit will become 1, indicating that there is an error in the received data. So we have one more register like THR, which is nothing but transmit hold register. Now it's the buffer register inside the transmitter. So if you want to transmit a character, then that character should be placed inside this THR. As I'm using UART 0, so that's the reason I have written U0 THR. So if you want to transmit a character, then that particular character should be placed inside the THR register. Now it's a transmit buffer register. And this is the syntax which we use, like here A is a character and that is placed inside the THR register. As I'm using UART0, so I'm using here U0. Now we have one more register like RBR, which is nothing but receive buffer register. Now this is related to receiver. Okay. So here you have two buffer registers, one is for transmitting and the other is for receiving. But as in case of 8051, we have only one buffer register, that is SBUF, for transmitting as well as for receiving a character. Okay, so here it's a receive buffer register. Now this is the syntax which we use, as we have to read from RBR register, so I'm using a character variable here. It might be anything, okay, and now it is reading, this character variable is reading the data present inside this RPR. As I'm using UART0, so I have written here it as U0 RPR. And then you have FDR register, which is nothing but fractional divider register. It's a 32-bit register, and out of these 32 bits, we'll be using only 8 bits in case of LPC2148. Okay, and here the first 4 bits are for divide val, and the next 4 bits are for mul val. Okay, so if you're programming these bits with possible values, then you'll get the accurate baud rate. Okay, we'll see how it is. See, in the previous case, we have assumed that this divide val as well as mul val term to be 0. Okay, and we have calculated a value into DLL and DLM for 9600 baud rate. Okay, now if you perform a reverse engineering on this, it means now we assume that we know this value, that is DLL and DLM. Okay, we know this value DLL and DLM. Okay, and we don't know for what baud rate we are calculating, so we don't know the baud rate. So what happens here? We know peripheral clock, we know DLM as well as we know DLL. Okay, and assume again this divide val as and mul val as 0. Now calculate the value, you'll get a baud rate more than 9600. Okay, so what is happening here is we are eliminating the fractional part inside this decimal. So that's the reason you'll get more than 9600. So if you want to get accurate 9600 baud rate, or if you want to use accurate 9600 baud rate, then you have to program these two fields, okay, with some sufficient values or possible values. Then you'll get the accurate baud rate. Okay. Now let us see how to write a program by using all the registers which we have discussed now. Okay. So what I'm doing here is I'm using a character A. So actually this is not required for this program. I want to transmit a character A. I want to transmit a character A by using UART0 for infinite number of times. So what I'm doing here is initially I'm configuring my GPIO pins which are provided for UART to act as UART pins like TX and RX. Okay, so I'm configuring P0.0 and P0.1 for serial communication. Okay, so in order to do that, I have to use pencil 0. So pencil 0 is now programmed with 0000 and 3 zeros 5. So it means now P0.0 and 0.1 are working as UART pins. It's nothing but TX and RX pins. And what I'm doing here, initially I'm configuring the control register. So U0 LCR equals 0x83. Now what happens here is, let us see that register. So if you can see this, now 83 in the sense 1 0 0 0. So it means I'm enabling this particular divisor latch. So what happens now? I can access divisor latch registers. Okay. Now this has completed 8 and 3 here is nothing but 0 0 1 1. It means I'm going with 8-bit character length. So I'm representing a single character with the help of 8 bits. Okay. So I've got 83. Now I'm placing the value which we have got earlier, that is for 9600, into DLL as well as into DLM. Okay. Now what I'm doing, I'm just making DLAP, that is the divisor latch access bit to 0. Now it has become 03, so that I can access the buffer registers THR as well as RBR registers. Okay. Now what I'm doing here is I'm checking whether the transmitter buffer is empty or not. Okay, so it means I'm monitoring this particular bit. I'm monitoring this TE-empty bit, whether this is empty or not. If this is empty, then it will become 1. Okay, so for that reason I'm using this particular condition. So I'm checking here whether TE-empty is empty or not. If that is empty, I can place a character into the buffer. So I'm doing the same thing here. I'm placing the character A into the buffer, that is U0 THR. Okay, so as you place this character, then what happens immediately, it comes here and then checks the while condition as this is true, and it waits here until that character is transmitted. Okay, so up till that, now what is present in this TMT bit, that is now 0. As soon as the character is transmitted, then this TMT will become 1. Therefore again it comes out of this while condition and then places one more character, that is again A. Okay, so my intention was to transmit this A for infinite number of times. Now that is achieved with the help of this program. Okay, let us see one more program. What I'm doing here is I'm just receiving the characters from the keyboard. Okay, after receiving the characters from the keyboard, and I'm transferring the same character onto the terminal. Okay, so I'm taking one character variable and configuring P0.0 and 0.1 to act as TX and RX, and then enabling divisor latch, along with I'm using 8 bits per a single character, and then I'm writing some values into DLL and DLM registers, which are used for generating the baud rate, and again I'm programming this LCR to 0x03, which means I'm now making divisor latch access bit to 0, so that I can access RBR as well as THR registers. So what I'm doing here, I'm monitoring whether the buffer, that is receive buffer, has received any character or not. Okay, so if it has received any character, then it will come out of this while loop, and so that we can read whatever the character or data which is present in this RBR register. Okay, and immediately I'm monitoring TMT bit. If that is empty, now I'm going to place this character into U0 THR. Okay, so after this again it comes to while 1, checks while condition as it is true. So what happens again, it will wait until a character is received. As soon as the character is received, then RDR bit inside the LSR register will become 1, so comes out of the while and then reads the character. Now it will again check whether the previous character was transmitted or not. If that is transmitted, then again it places the character into U0 THR. Okay, so this is how we write programs for UART 0 or UART 1. Okay, the only difference between UART 0 and UART 1 is that UART 1 is provided with some additional signals like modem signals are also provided for UART 1. But when it comes to UART 0, it has been provided only with serial communication pins like TX, RX, and